All right, so today we're talking about concentration. And so concentration in a solution is basically the ratio of the solute to solvent. The ratio of solute to solvent, right? So in other words, how much solute do you have dissolved in your given amount of solvent? So for instance, if we have two beakers, let's say they're both 500 mils. And this one's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, just for fun. 1, 2, 3, 4, 5, right? This one's got 25 solute particles, whereas this one's only got 5 solute particles. Right? This one is 5 times more concentrated. Right? The ratio of solute to solvent is called concentration. So if I were using a real world analogy, right? If I added more water to this, would that make it more concentrated or less concentrated? It would make it less concentrated, right? So concentration is just the ratio of solute to solvent. If you've got the same amount of solvent in both beakers, one of them's got 25 particles, the other one's got 5, right? This one's 5 times more concentrated in the same given amount of solvent. Does this make sense? Now there are some units of concentration that we use to express this ratio quantitatively. Because obviously you're not going to be able to see the particles to sketch a picture of that ratio, but we can calculate it. There are units of concentration. And so I'm going to list them all out. I'm going to go over some examples, and then I'm going to give you some to do. And then we'll go over those. Units of concentration.
I want to read my book.
Okay, it's back there. Okay, so units of concentration. First one we're going to talk about is called molarity. Molarity. And we represent it with an uppercase M, and I underline it. And the reason why I underline it is so that you can tell it apart from something very, very, very similar, a word that sounds extremely similar, which is called molality. We'll talk about it in just a minute. So I underline it just so that you can tell, especially if I'm writing it by hand, hey, that's an uppercase M, okay? And the way we calculate molarity is moles solute per liter solution. So in other words, the units are moles per liter. Moles per liter. Okay, molarity, moles per liter. And so when we're doing a lab, right, you would see capital M's written next to, you know, you'll see a beaker that says 2.5 M. That's what we're referring to here. So if you've ever seen a capital M next to something, that's what it's referring to, molar concentration. Number 2. Let's go ahead and talk about that one that I was referring to, molality. We represent that with a lowercase m. Okay, that's why I underline to differentiate between molarity versus molality. This one is moles solute per kilogram solution. So its units would be moles per kilogram. Moles per kilogram. So molarity is moles per liter. Molality is moles per kilogram. Okay? So notice these two look really similar and are spelled really, really similar, but they mean something very, very different, right? One's moles per liter, one's moles per kilogram. And I'm going to show you examples of both, just to make sure. And again, you don't have to underline it, but I always do, just to be safe, right? So that, especially if I'm handwriting it, I communicate, hey, that is an uppercase M. Because some people, you know, you write your uppercase M's kind of rounded, and that gets you into trouble. So,
I already read my book. Thank you.
So, I always underline it. All right, let's talk about a couple that you may have already seen out in the real world. Parts per million. Which we represent as ppm, parts per million.
Your voice is way too loud.
Okay, so this is, now the units here really don't matter so long as they're the same, okay? You could have it in grams, you could have it in milligrams, you could have it in kilograms, just as long as they're the same units. So it is the mass of solute over the mass of solution. You take that number and then you multiply it by 10 to the 6th. 10 to the 6th is the same thing as a million, right? And again, the note here is that units must match. Okay? Because if you take grams and divide it by kilograms, that's going to give you a nonsense answer. So make sure that your units match for parts per million. And you may have seen that one out in the real world before too. And now parts per billion, ppb, oops, that's number 4. Parts per billion, we represent that as ppb. It's the exact same way we calculate parts per million. Mass of solute over mass of solution, but this time we're multiplying it by what? What would that be? Does anyone know? What's a billion? 10 to the 9th, right? Mass of solute over mass of solution. Times 10 to the 9th. And again, make sure that your units of mass match each other. If one's in milligrams and one's in kilograms, your answer is going to be totally nonsense. Right? Your answer won't make any sense. So parts per million and parts per billion are calculated the exact same way. The only difference is what we're multiplying by. Okay? Multiply by 10 to the 6th, multiply by 10 to the 9th. Got 2 more to add to this list. Is everyone okay if I erase these first 4? So once we go through all our definitions, I'll give you examples of each one, and then I'll give you some to try, and then we'll go over those. Because my goal is that you always try some while we're in class. So if you get stuck, you can work it out. Okay, the next one is called percent by mass. And it's represented percent sign, and then you usually see M/M. It means percent by mass. Okay, so this is mass of solute over mass of solvent. Notice, oh, excuse me, not mass of solvent, mass of solution. Now, the key word here, I forgot to write, is total. Total mass of it. Yes?
I can't play all of it.
And then this is times 100. All right, 6, and the last one is percent by volume, which is percent V/V. And again, this is mass, oh, not mass, volume of solute over total volume of solution times 100. Percent by mass, percent by volume. So let's start by doing some examples of these two, because these are the two that I already have up on the board. So let's do an example of percent by volume. If you understand percent by volume, you'll understand percent by mass. So let's do an example. You dissolve 50 milliliters ethanol, which has the formula CH3CH2OH, in 100 milliliters water. What's the percent by volume? You dissolve 50 milliliters ethanol in 100 milliliters of water. Is the identity important here? Do you need to know that it's ethanol and that it's water? Or could you just say you dissolve 50 milliliters of solute in 100 milliliters of solvent? Does the fact that it's ethanol mean anything to the calculation? No, because we're not converting to moles, right? If we were converting it to moles, obviously you need to know the identity. But just so we can identify it, what is the solute? The solute here is ethanol, right? How did I know it was the solute? All right, the smaller amount is always the solute. And the solvent would be H2O. So the percent by volume, what number is going to go on top? The volume of the ethanol, so 50. Now, here's what gets students in trouble. Does the bottom number 100? Are you sure? 150, right. Why is it 150? Because it's the total volume. Okay? I write lots of multiple choice questions where I could make an option where it could be 50 over 100 or 50 over 150. Which one's the correct answer? 50 over 150, right? It's the total volume. So milliliters cancel, so this doesn't have any units. Your units would just be percent. So 50 divided by 150 gives me 0.33333333333. Now multiply by 100. And then how many sig figs can I keep? This number's got 3. This number's got 4. So how many sig figs? 3, right? And then my unit would be percent. That makes sense? See how to do that one? Does everyone see why it's 50 over 150 and not 50 over 100? Because it is total volume. Make sense? Let's do one involving percent by mass, since I've got the formula still up on the board. Is everyone okay if I erase this one? Okay. So let's do this one. All right, let's do one involving percent by mass. you dissolve 95 grams sugar in 200 grams water. What's the percent by mass? Dissolve 95 grams of sugar and 200 grams of water. Again, is the fact that it's sugar bear anything on the calculation here? No, it could be anything, right? As long as it dissolves, it could be anything. So, calculation would be, what goes on the top? 95. What goes on the bottom? 295, right. Again, why is it not 200? Because it is total mass of solution. And then we multiply that by 100. Grams cancel, so my units are just going to be percent. Now make sure your units match. Obviously, if one was in grams and the other one was in milligrams, you'd have to do some converting. So let's do this math. 95 divided by 295. My calculator times 100. My calculator spits out 33.2033839999, right? How many sig figs can I keep? This number's got 3 sig figs. This number's got 4 sig figs. So what do? 3 sig figs, right? So 32.2, and my unit would just be percent. All right, before I go on to any other ones, I'm going to put on up on the board for you to try. I'll pause the recording while I let you try it, and then we'll go over it. So use your formula to figure out which one to use. I dissolve 125 milligrams salt in 1.0 gram. Actually, let's not make it 1. That's too easy. Let's make it 2.50 grams water. What's the percent by mass? All right, I'm going to pause the recording, let you try this one. Okay, what little detail do we need to watch out for in this problem?
Is that better?
Yes, that's better. Thank you. You have to have what? Ones in milligrams, ones in grams. Right. So does it matter which one I convert? No, so long as you're consistent, right? I could convert milligrams to grams, or I could convert grams to milligrams. It doesn't matter which one I convert so long as they're the same, right? So I'm going to convert milligrams to grams just because that's what I picked. If you converted grams to milligrams, though, that would have worked the same way. How do I convert milligrams to grams? 125 milligrams. Let's set up a conversion factor. How many milligrams are in a gram? 1,000. So I divide by 1,000. That's just moving the decimal 3 to the. Moving it 3 to the left, right. So that'll be 0.125 grams. So now I've got grams and I've got grams. Am I ready to do my arithmetic? Yes. So percent by mass would be, which number goes on top? 0.125, right. 0.125. And then what goes on the bottom? 2.5? Or is it 2.625? How did you get that? You have to have the total mass, right? The denominator is the total mass. Is this going to be a very concentrated solution? We would not classify this as very concentrated, right? Because there's not a whole lot of solute in here, is there? So when we do our math, 0.125 divided by 2.625, and then times 100, gives me 4.7619, da 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 da. How many sig figs am I keeping here? 3 sig figs. So my final answer would be 4.76%, which is not very concentrated, right? I'm going to give you another one to see if you can work backwards and figure it out. Thank you. Is everyone good on this one? All right. Let me give you one to try and see if you can figure this one out, because I think there's one like this in the homework. Almost certain there is. You have a bottle of 3.0% hydrogen peroxide solution with a total volume of 350 mils. How much H2O2 is dissolved in the solution? I'll pause the recording. Okay, so this time we're figuring out how much solute is in the solution, all right? We're not solving for the concentration. We already know that. We're solving for the amount of solute. So we're just using our formula. If percent by mass, oh, this is percent by volume, though, isn't it? Because it says the volume. If percent by volume is the volume of solute over the total volume times 100, we can just plug our numbers in and solve for x, right? So 3%, let's go ahead and convert that into a decimal. What is 3% as a decimal? 3.0% is the same thing as 3.0 over 100, right?
I can't see now.
I know. You have to wait just a second. 3 divided by 100 is what?
0.003.
Right. Just move the decimal 0.03. Right? And then don't forget that sig fig. So 0.030 is equal to, we're solving for this, x over 350. Now don't forget that this is being multiplied by 100. Right? So the first thing we have to do is, we've technically already done that, so I can drop this part. We've already divided by 100, so we don't need this times 100 anymore. All right, so to get x by itself, multiply both sides by 350. So x is equal to 0.03 times 350. That's 10.5. And my unit would be milliliters. Is that a reasonable answer? You can always check your work, right? 10.5 divided by 350 gives me my 3% back. So you can always check your work. So if you buy a 350 milliliter bottle, you're actually only buying 10.5 milliliters of your actual solute, whatever that is. All right, let me give you another one to try before we move on to practicing the other ones. If you want a 5% solution with, let's say, I don't know, 25 milligrams salt. How much water should you use? All right, pause the recording and let's try that. All right, camera focus, please. There we go. So, you know you want to make 25, you know you want to use 25 milligrams, you know you want it to be 5%. How much water should you use? So we're solving for the same thing again, right? 5% this time is equal to 5% is the same thing as 0.05.
It's all videos and roller games.
Okay, that's fine. You do it.
Play the wall games.
Go. 5% is equal to, this time it's 25 over x, right? And this is being multiplied by 100, so we have to undo the times 100 part. What's 5% as a decimal? Right, 0.05 is equal to 25 over x. Okay, so multiply by x to get it out of the denominator. 0.05x is equal to 25. Right now get it by itself. So x is equal to 25 divided by 0.05. 25 divided by 0.05 gives me 500. Now, be careful, because is that how much water I should use? No, that's the total. That's the total amount, right? This equals the total mass. What mass of water should I use? You got to factor in the 25 milligrams of whatever your solute is, salt. Right? So the mass of water would be the 500, and we're keeping 2 sig figs. Let's make it 3 just so that I can keep that decimal place right there. Minus 25. So that would be 475 milligrams H2O. Does everyone see why we had to subtract out 25? Because this is the total mass, right? What we solved for is the total mass. We need to get the mass of the water, which means we got to subtract out the mass of whatever our solute is. Does this make sense? Any questions on this one? We good on these kinds of problems? All right, let's do some examples on molarity, molality, and percent by, parts per million, parts per billion, that sort of thing. So let's do some parts per million and parts per billion examples, because those two kind of go along together. ppm and ppb examples. Because if you can do parts per million, you can do parts per billion because they work exactly the same way, right? The only difference between parts per billion is you're multiplying by 10 to the 6, we're multiplying by 10 to the 9. That's the only difference. So let's do an example. A 5 kilogram sample of soil contains 17.5 milligrams arsenic. That's probably not something you want in your soil, right? What is the ppm concentration. Now, the formula, ppm is equal to the mass of the solute over the mass of the solution times 10 to the 6th, right? We've got kilograms and we've got milligrams. Can we go ahead and do this as is? No, we can't, right? We have to have the units be the same. So, why don't we just convert them both to grams? Or you could convert milligrams to kilograms. I don't really care how you do it. Just be consistent, okay? 5 kilograms. I think it's good to practice unit conversions. Let's just convert them both to grams. 5 kilograms. There's 0.001 kilograms in every 1 gram, right? So we're moving the decimal 3 to the right, 1, 2, 3. So that would be 5,000 grams. And now let's convert milligrams to grams. 17.5 milligrams times 1,000 milligrams per gram. So now we're moving the decimal that way. So 1, 2, 3, 0.0175 grams. Now my units match. And now I'm able to do my arithmetic. Do we agree? So ppm is equal to, which number goes on the top? Which one's the solute, which one's the solvent? This is the solute, right? That one's arsenic. And then this is soil. So which one's the solute? Yes. The solute is always the smallest one. Yes. So this is our solute. And this is our solvent. So 0.0175 grams total. Now, if you forgot to add this 0.0175 to 5,000, is that going to really impact your answer? No. We'll do it just because, but if you forgot to add it, 5,000 versus 5,000.0175 is not going to make a huge difference, right? Divided by 5,000.0175 grams times 10 to the 6th. Grams cancel. So 0.0175 divided by 5,000.0175 times 1e6. So this is, and how many sig figs am I keeping? That one's got 3, that one's got 3, so this one's got 3. So 3.50, and my units would just be ppm. You see why we had to do these conversions first? Because it's not very pragmatic to measure soil samples in milligrams unless you're literally going out and just taking a little tiny pinch, which you could. But I'm imagining like a big bag, right? That'd be a 5 kilogram bag. So 3.5 ppm. We're going to use parts per million, as the name implies, when we've got small concentrations, right? We were hoping that the amount of arsenic is small. And I don't know what the actual arsenic concentration in soil is. I'm hoping it's way lower than that, though, because that's still pretty high for something that's poisonous. Any questions on how we do this? You want to try one? Or try one for yourself? All right. A 100 liter sample of water contains 0.83 milliliters. What's something we can use? Pb2 plus. Lead is not something you want in water. What's the ppb concentration? I'll pause the recording and let you try that one. Okay, so we've got a 100-liter sample of water, and it contains 0.83 milliliters of the lead 2 ion. What's the concentration? Can we do this with one unit being in liters and one unit being in milliliters? No, it won't make sense. So let's convert liters to milliliters or milliliters to liters. It doesn't make a difference. What did you do? You did milliliters to liters? Okay. 0.83 milliliters. How many milliliters are in a liter? 1,000. So when you do this, how many decimal places are you moving? In which direction? Right, 3 to the left. So 1, 2, 3. So that gives me 0. Fill it in. 0.0083 liters. Are we ready to do the calculation now? Okay, what's the solute? What's the solvent? Solvent is water, and it's got a mass of 100, it's got a volume of 100. And then the solute is the lead. All right, so which one goes on top? The lead. So 0.00083 liters over, what goes on the bottom? 100. Let's just put 100. Because is there going to be a significant difference between 100 and 100.00083? No. There's not. I mean, if you want to be scrupulous, you can write it out, but I promise you, there's not going to be a significant difference. So, just for fun, we'll calculate it both ways. 0.00083 divided by 100.00083 gives us, and then times 1 plus 10 to the 9. $829.93, which will keep 3 sig figs or 2 sig figs, would be 830 ppb. If you do it without the 100, you're just moving the decimal 2 over. Doop, doop. So 0.00083 divided by 100 times 1/9. I left off a decimal place somewhere, didn't I? 0.00083 divided by 100.00083 times 1/9. Yeah, I left off a decimal place. My decimal in one place. 8299.3, which rounds to 2 sig figs, 800 and 1, 2, 3. Did you get the same number? I left a decimal place the first time. You get the same answer regardless. Is that a concentration you want to be drinking? No way. No, 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 no. That's really, really high. In my town, the city sends out a water quality report every year. It's usually in this time of year. We got it, I think maybe in August or September. And it sends out water quality report for the city's water supply. And it tells you all of these pollutants and what their concentrations are and what the EPA says is okay and what the value in the sample was. And ours is always way below, if not zero, what the EPA says. So if you get your water quality report and it says this, you need to think about moving because that's really dangerous, right? You would start having some serious problems if you're drinking water with that high. I just made these numbers up, obviously. That's not good either. Lead, you can test for lead in your water at home really easily because if you just put some salt in your water, if it contains lead, you'll see a bright yellow precipitate. So you'll see it turn this yellow solid at the bottom. We're actually going to talk about how to do that very soon. I'm not going to do it on Wednesday. We'll do it next week. All right. Let's do one more kind of problem with parts per million and parts per billion before we do some examples of molarity and molality. Okay. Let's do 50 milligram, actually, let's not do milligrams. Let's do grams. A 50-gram sample of rainwater has a sulfate concentration of 19 parts per billion. What mass of sulfate is in the water? I'm going to pause it and let's try this one. Okay, so this time we're solving for a different variable. 50-gram sample of rainwater has a sulfate concentration of 19 parts per billion. What mass of sulfate is in the water? So if parts per billion is equal to mass of the solute over mass of the solution times 10 to the 9th, right, because this is parts per billion, we're just going to plug in and solve for the variable that we're missing. So 19 is equal to x, that's what we're solving for, over 50 grams times 10 to the 9th. All right, so what do I need to do to get rid of the times 10 to the 9th component? Divide both sides by 10 to the 9th. So 19 divided by a billion. You can enter that in your calculator, by the way. It's going to give you a very small number. 1,9 divided by 1e9. That's going to put it in scientific notation for you, right? So 1.9 times 10 to the negative. Actually, mine did it. 1, 2, 3, 4, 5, 6, 8. 8 is equal to x over 50. Do we agree on how we got rid of that first part? Now we're going to multiply both sides by 50 to get rid of the denominator. So x is equal to 50 times that value. So that gives me 9.5 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. And my unit would be grams. Is that reasonable? Would you expect a very, 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 very small amount to be dissolved? If the parts per billion concentration is 19, you'd expect that to be a very small answer. And if you get some big giant answer, you know you made a boo-boo somewhere. Do we agree on the answer and how it was obtained? Yes? All right. Do we feel pretty good about parts per million and parts per billion? If this were parts per million, this calculation would have been done the exact same way, except we would have been doing 10 to the 6th right here instead of 10 to the 9th, right? It's exactly the same for parts per million and parts per billion. The only difference is 10 to the 6th versus 10 to the 9th. So parts per million and parts per billion go along together. Percent by mass and percent by volume go along together. Let's do a quick one on molality. We're not going to deal with molality a whole lot, but let's do one just so that you have an example or two. All right. You dissolve, what's the number we haven't picked? 22.3 grams KCl in 110 milliliters water. What's the molality? Now let's refresh our memory on what molality's formula is. Molality is moles solute over kilograms solution. So what's the solute here, water or KCl? The solute is, which one's the bigger number? Water, so that means that the solute must be KCl, right? KCl is always, the solute's always the smaller number. Now this is mole solute, so can I just put 22.3 and be off to the races? No, what do I have to do? I have to convert it to moles, right? So let's do a side calculation. I'm still on the screen here. Yes. Okay, molar mass of KCl. Let's do a calculation of that. Potassium's molar mass is 39.098. And chlorine is 35.45. Right, so we have to calculate molar mass. 39.0983 plus 35.45 gives me 74.4898 grams per mole. Now let's convert grams to moles. 22.3 grams KCl. Is grams going to go on bottom or on top? On the bottom. So 74.4898 grams per mole. So grams cancels. So 22.3 divided by 74.4898. Carry out extra decimal places because we'll round at the end. 0.2982 moles. Do we agree on how we converted grams to moles? And now we have to do a second calculation. We have to deal with the water. Right? We have to deal with the water. So that's the part dealing with the KCl. We also have to deal with the water as well. 1 milliliter of water has a mass of what? Does anyone know? This is only special for water. 1 milliliter of water has a mass of 1 gram. That's a unique property of water. Its mass and its volume are the same because its density is 1 gram per milliliter. That's something you can only do for water. You can't do this for other substances, but for water you can. So therefore, 110 milliliters is equal to 110 grams. That's something you can only say for water. Water's special. So if we've got milliliters, we've got to convert it to grams, but that's the same thing as its milliliters, okay? You can only say that for water. Otherwise, you have to multiply by the density. So 110 grams of water. How many grams are in a kilogram? 1,000 grams per kilogram. So we're just dividing by 1,000. So that's 0.1100 kilograms. Now I've got everything I need to be able to do this arithmetic, right? So the molality is moles, so 0.2982 moles, and the kilograms, 0.1100 kilograms. So divided by 0.11, rounding to 3 significant figures. So that would be 2.71, and my units would be M, or you could write it as 2.71 moles per kilogram. You have choices. And that's all we're going to do with molality. We don't do a whole lot with molality in intro chem. If you take general chem later on in your career, we'll do a lot more with molality. But with intro chem, that's all we do with it. That's as far as it goes. Does everybody understand how we did this one? Okay, the last concentration unit we need to deal with is molarity, and we're going to do several kinds of molarity calculations. Because we can do a lot with molarity. That's why I'm doing it last. So let's do some molarity examples. If 35.5 grams MgCl2 are dissolved in 250 milliliters water, what's the molarity? Just barely stayed in the frame there. If 35.5 grams magnesium chloride are dissolved in 250, let's put a decimal place there, just for sake purposes, milliliters of water, what's the molarity? Okay, so molarity is equal to moles over liters, right? Do we have everything we need to go ahead and do that division? Can I just say 35.5 divided by 250? Is that something I can do? No, I can't. What do I have to do first? Convert grams to moles, and then what do I have to do to that volume? Convert milliliters to liters, right? So I've got to do 2 conversions first. So let's deal with the moles part first. Before we can do grams to moles, what do we need? Molar mass, right? So magnesium chloride, am I still in frame? MgCl2. Let's calculate its molar mass real quick. So magnesium is 24.305, and chlorine is 35.45. We've got 2 of them. So when we do that, I got 95.205. Did you? So now let's convert that grams to moles. 35.5 grams. Grams go on top or on bottom? On the bottom. So 95.205 grams per mole. Carry out extra decimal places because we're going to round later. I got 0.3729. So that's 0.3729 moles. And then what do I do with this milliliters? What is that in liters? Do I need to write out the conversion factor, or can we do it in our head? You want to write out the conversion factor? What would that be in liters? Let's just do the math, just to make sure. 250 mils. How many milliliters are in a liter? 1,000. So we're just moving the decimal 3 to the left. So that's 0.250 liters. All right, so let's do our dividing. Divided by 0.25. Keeping 3 significant figures would give us 1.49. And in terms of units, you could either write capital M or you could write 1.49 moles per liter. So I don't care how you write the units. You can either write capital M or you can write moles / liters, whichever makes you happy, because they're both acceptable. You ready to try one? I'm going to make you think. I think your brains are warmed up enough now that you can do one without me showing you an example of this kind of problem first. You try this one. You want 500 milliliters of a 1.25 molar NaCl solution. What mass of NaCl should you dissolve? Pause the recording and give you a chance to try that one. Okay, so you want to make it 500 milliliters of a 1.25 molar solution. What mass should you dissolve? So here we have to use the molarity equation to solve for an unknown, right? Molarity is equal to moles over liters. Is mass part of this equation at all? Focus, please. Focus, please. There we go. Is mass part of this equation at all? No. So what can we solve for? What's our master strategy? We need to solve for what first? Moles, right? And then what do? Convert it to grams. Okay, so let's plug in the information. 1.25 is equal to X over, can we leave that in milliliters? No, what do we need to do? Convert it to liters. So 500 milliliters is how many liters? 0.5, right? We're dividing by 1,000, 1, 2, 3, so 0.5, and then don't forget those sig figs, 0, 0, 0. So to get that by itself, got it in 0.5000 times 0.5000. So X equals, I'm just going to take half of that, 1.25 times 0.5, right? So 0.625, 0.625 moles of NaCl. That's great, we've got moles, but the problem asks what mass is dissolved. So what do we need in order to do that part? What do we need now? We need to convert moles to what? To grams, right? Which means we need to have the molar mass. Yes, so let's calculate the molar mass off to the side. Oops, it's not in, it's in. NaCl has a molar mass 22.99 plus 35.45. So 22.99 plus 35.45 gives me 58.44 grams per mole. So 0.625 moles times, where's grams going to go, on the top or on the bottom? On the top, right. We're converting to grams, so 58.44 grams per mole. Moles cancels. So times 0.625. And then we keep 4 sig figs, 3 sig figs, so 3. So 36.5 grams. All right, so you'd measure out 36.5 grams on your balance. You get yourself 500 milliliters of water, dump it in, you stir, 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 and that would give you the molarity that you want. How do we feel about this? How do we feel about this? We've got one more kind of calculation to deal with molarity. It's really quick. I think I'll only need to do one example of it, and then you'll probably have it. So let me go over that one really quickly. It's called dilution. So dilution you're taking a solution and making less concentrated. So for instance, I've been drinking out of this all class period. I drink about a third of it, right? If I top that off with water, would that make it more dilute or more concentrated? More dilute, right? It wouldn't taste as grape-like, right? That's the same thing that we're doing here. When you add more solvent, you're not adding more solute, right? Because if you add more solute, that would make it more concentrated, right? If I wanted to concentrate this, I'd either boil off the water or I would add more mixture, whatever, sugar and grape flavor and all that stuff. To make it dilute, I would just add more water to it, more solvent. So the equation is M1V1 is equal to M2V2. Well, these are the molarity and volume of the concentrated, and these are the molarity and volume of the dilute. All right, so M1V1 is equal to M2V2. So we're just making this solution less concentrated. So I'm just going to go through one example. I think if you see one example worked out, you'll probably be good, because these calculations aren't very hard. So let's do an example. You take 25 milliliters of 10 molar KBr solution and dilute it to a new volume of 150 milliliters. What's the new concentration? So it starts out at 10 molar. What's going to happen to that molarity? Is it going to go up or down? Taking 25 milliliters, and you're diluting it to this much space, what's going to happen to the new concentration? It's going to be higher than 10 or lower than 10? It should be less than 10, right? So let's just list out our variables. M1 is 25.0 mils. V1 is 10 molar. M2, that's what we're solving for. V2 is 150 mils. Now, so long as your volumes are the same, I wrote that in the wrong spot, didn't I? All right, those two backwards. 10 goes here, and 25 goes here. So long as your volumes match, that's all that matters here, okay? If this one was in liters and this one was in milliliters, that would be a train wreck. But because these two match, we don't need to do any converting already. Right? They're the same. All right, so let's plug in and do our arithmetic. M1 V1 equals M2 V2. 10 times 25 is equal to X times 150. Okay, so 250 is equal to 150X. So divide both sides by 150. So X equals, just do your dividing. 250 divided by 150 gives you 1.666667. We're keeping 3 sig figs here, so that would be 1.67, and my units would be molar. Does it make sense that the molarity went down? It should be, right? Because if you take 25 milliliters and then you increase the volume now that it's 150 milliliters, that's going to spread out and become more dilute, right? Imagine like when you take a drop of food dye and you drop it into a big beaker of water, right? It spreads out. That food dye is really concentrated and it spreads out, now it's dilute. Do we feel good about dilution calculations? All right, that's where we're going to stop for today.